Let's talk about scientific notation. Today we're just going to introduce you to how numbers can be written in scientific notation and give you an idea of why. So you can see we have one very large number and one very small number, lots of zeros to keep track of. And scientific notation is a way to represent those numbers so that they don't have as many zeros, it's not as tedious, and it's easier to kind of identify what numbers are larger or smaller when you're comparing numbers in scientific notation rather than in standard notation, which is what this is called. All right, so let's look at some examples of numbers in scientific notation and numbers that are not in scientific notation. And let's just see if we can figure out what is happening with each of these. So in the scientific notation column, you see numbers being multiplied with powers of 10. I see a couple of numbers being multiplied with powers of 10 over here also. So that's not the only thing that makes numbers scientific notation. There's got to be more to it. And when you start to look at where the decimal is sitting in each of these numbers compared to where the decimal is sitting in these two, you might notice that here we have one digit to the left of the decimal, one digit to the left of the decimal. We still have one digit to the left of the decimal here. We're just too lazy to write that decimal. It's sitting right there. So each of these has one digit to the left of the decimal. This one has 3 digits to the left of the decimal. Again, it's sitting right here. We're just too lazy to write it. But this one only has 1 digit to the left of the decimal, so why is it not in scientific notation? And the answer is because it's a 0. So with scientific notation, you can only have 1 digit to the left of the decimal, but it can't be 0. And you also express it as a power of 10. This number up here is in what we call standard form. Standard form being what we normally use when we talk about numbers. So standard form here, these two, not scientific, not standard form, but still representing the same values. So this number represents this number. These two are equivalent values. These two are also equivalent values. These are in scientific notation. These are not. This one's in standard notation. All right, so you might want to take a moment and write this down just to kind of help you have an idea of how to get started with writing numbers in scientific notation. So you're going to write it as a product of a number that has 1 digit to the left of the decimal, not 0, and a power of 10. So let's look at an example. In 2019, the United States minted nearly 11,900,000,000 coins. Express this number in scientific notation. So currently the number is in standard notation, 11,900,000,000. And it's not a bad number to say, it's not a bad number to recognize or a challenging number to recognize. But once you start mixing in other numbers, like maybe you might be trying to find how many coins the US minted in a decade or in a century, you start working with larger and larger numbers and it just becomes tedious. So scientific notation becomes useful. So what we need to do is remember that we can only have 1 digit to the left of the decimal. Right now the decimal is sitting right here. So we need to move it so that it's sitting right here, so that there's only 1 digit to the left of it that is not a 0. We need to keep track of how many times we are moving the decimal so that we can represent that as a power of 10. So let's go ahead and move it from here to here and just count. You can do groups of 3 if that's helpful for you, or you can count them individually. So you could go 1, 2, 3, or you could go 3, 6, 9, and one more makes 10. So we will need to move our decimal 10 places to represent 11,900,000,000 in scientific notation. So let's go ahead and write down where we're putting it. And once you finish writing down the digits that are present, that are followed by a bunch of zeros, you can drop all those zeros. That's the whole point. We don't want to write all those zeros. So we've shown where we're moving the decimal to. Now we need to represent how many times we moved it to get it there. And that's where we multiply by a power of 10, because powers of 10 are how we move our decimals. And in this case, we move the decimal 10 places. So our power of 10 is positive 10. It's a positive 10 because our original number in standard notation is a large number. Large numbers are represented with positive exponents on our powers of 10. Smaller numbers, which we'll look at next, are represented by negative exponents on our powers of 10. So again, find your decimal in your original number, find where you need to place it so that there's only one digit to the left of it, and then count how many times you're moving that decimal. Write down what you have, where your decimal is sitting, and then multiply by a power of 10 with that power representing the number of places you moved your decimal. Let's look at a small number next. All right, so here's a great example of where scientific notation definitely makes it easier to work with a number. The diameter of an electron is about that tiny number of meters. I don't even want to try to say it. I don't want to find the place value. That's just a lot of zeros. Seems like really tedious and not a lot of fun to work with. So we are going to translate this number into scientific notation. We're not going to change the value of the number. It just makes it a lot easier to work with. So currently it's in standard notation. All right, so I've placed it in the standard notation column, and we need to translate it to scientific notation. So decimal sitting right here. There's one digit to the left of it, but it's a 0, and we can't have a 0 in front of the decimal if we're putting it into scientific notation. So we need to go ahead and move this decimal until there is only one digit in front of it that is not a 0. And that is going to be moving it this direction until it gets to right there. So our first thing that we're going to write for our scientific notation is 2.82. We're going to be moving the decimal right there. We need to figure out how many times we've moved the decimal so we know what power to put on our power of 10. So let's go ahead and count. And again, you can count individual spaces. Sometimes when you have this many zeros, it ends up being kind of tedious and you might make a mistake. So that's why, again, I like to use groups of 3, but do what you need to do for you. So I'm moving it 3, 6, 9, 12, 15 places to get from where it is in standard notation to where it needs to be for scientific notation. And if you counted these all individually, it would still be 15 places. So what's different about this one from the last problem is that we are not working with a large number in standard notation. We're actually working with a very, very tiny number. And so if we put a positive 15 on here and somebody tried to recreate our standard notation using only this, they would be creating a very large number. So we need to let them know that what we're working with is a small number. And if you use a negative exponent, hopefully you remember that 10 to the negative 1 represents 1/10. 10 to the negative 1 means that this belongs in the denominator. Currently, it's in the numerator. So you move it to the denominator and make your exponent positive. And sitting on top is a 1. We don't leave nothing behind. And so that's just 1/10. That's a small number. If we have a negative 2, it becomes 1 over 10 to the second, which is 1/100th, and so on. So we're getting smaller and smaller. We moved this 15 places. It's a small number, so we use a negative 15 to represent how many places we move the decimal in the standard notation to create the scientific notation. All right, let's do one last example just to compare a large number and a very small number and how we write them in scientific notation, going from standard form to scientific notation. And then in our next video, or in my next video, I will be talking about how to move from scientific notation back into standard notation. So let's start with these two and compare them. So here we have a large number. The decimal is sitting at the end. We want to put it into scientific notation, which means we need to have one digit in front of the decimal that is not a 0. So if the decimal is starting here, we are going to move it right here. And we need to count how many places we're moving it. You can count each individual space or you can count by threes. That's your decision. So I like to count by threes. So there's 3, 6, one more space means I am moving it 7 spaces. So the decimal lands right here. Even though this is a 0, we do need to write it because we have another significant digit or digit other than 0 that we need to represent. If we drop that 0, it changes the value of the original number compared to the number you're writing in scientific notation. So you write all the numbers that you have until you get to the remaining zeros, and then you can stop. So we need to write down 1.07. Do not drop that 0. We're multiplying by a power of 10. We have a large number, so our power of 10 is positive. And in this case, we moved it 3, 6, one more space makes 7 places. So large number in standard notation means you have a positive exponent. On your power of 10. Over here, we have a very small number. The decimal sitting here. We need to move it until there's one digit in front of it that's not a 0. So it's going right here. We will again have 1.07. Do not drop that 0. We need it to represent our original number equally in scientific notation. Let's count how many places we're moving the decimal. 3, 6, one more makes 7. But now we have a small number. Because our number is very small, we need to represent that with the negative exponent. 1.07 times 10 to the negative 7 means we have a very tiny number. 1.07 times 10 to the positive 7 means we have a very large number. So here we have a small number in standard notation gives you a negative exponent. Hopefully that's helpful. Definitely something I think about as I work with scientific notation and standard notation, which you'll see in the next video.